So our final option for atomization techniques is an inductively coupled plasma, or an ICP. And you'll often see these paired as an optical emission spectrophotometer, but you may also see this paired with a mass spectrometer as well. But either way, this is simply a way to get your sample into the gas phase, well, with a nebulizer, and then atomized, and potentially ionized, which is why it ends up working well with mass spectrometry. But we'll get into that later in this course. So with an ICP, the way that this works is you're going to have a series of concentric tubes. And so I'm going to draw these in different colors so hopefully we can distinguish between each tube. Okay, so the first tube that I'm going to draw here, right in the center, this is the narrowest of the tubes. Okay, so we're going to draw tubes around these. And in this first tube, this is where we're going to put the sample in. And the way that we put the sample in is we're going to have nebulized it using the same kind of nebulization technique that we saw with atomic absorption, with the flame atomizer, but we're going to have it be mixed with argon. Okay, so it's got some argon flowing through here with the nebulization. All right, so then the next tube surrounding that tube is called the plasma tube. Okay, I'm going to draw this. It comes up rather along the same plane as this one. And this one is the plasma tube. And the plasma tube is feeding high purity argon into this system. And what this high purity argon is doing is it's continuing to make sure that our sample is being nebulized into the gas phase, that we're not it's not forming more droplets. It's going to keep pulling the sample up the tube and nebulizing it into those very fine droplets that are going to dry and be able to be atomized very easily. All right, moving outward from the plasma tube is going to be our coolant tube. I'm going to draw that one in black. Okay, and that one is around these other tubes. So this is a coolant tube. And this one also uses high purity argon. And what the coolant tube is basically going to do is to add cooler argon coming up to where we're not going to get our plasma to be completely uncontrolled. So when we have our argon coming up from our plasma tube, in addition to nebulizing the sample, this is what's going to form our plasma. Okay, and what is a plasma? A plasma is simply a gas that's hot enough to have both ions and free electrons. Free electrons. Okay, and so what is our ion that's going to be floating around? Well, one of them that we're going to do is we're going to take argon and we're going to ionize it. Now, if you remember from your general chemistry, and we talked about argon as a noble gas, it doesn't freely give up electrons. It takes quite a bit of startup energy to make that happen. So we'll actually ionize it starting with a spark in order to get this to initially ionize, and then once a plasma is formed, it will continually form through radical reactions with the free electrons that are now present. Now, what else happens in here? Well, in addition to this coolant argon that's kind of keeping the plasma contained in the center of the tube, the coolant tube, around that tube is also an induction coil. So this is surrounding our tube. This is our induction coil. And the induction coil is going to apply a radio frequency field that's going to accelerate our free electrons. So as these free electrons are then continually colliding with atoms, it's transferring energy to them and exciting them. And so like we talked about in our introduction video to this module, you can have excitation in ways other than through the absorption of light. And this is one way that you can excite atoms, is through this collision with these free electrons. So as it excites all of your atoms, then we get our excited atoms ready for atomic emission. One other thing that I want to note is that plasmas are incredibly hot. Okay, when we talked about flames, we talked about them being about 3,000 Kelvin. The plasma is running typically closer to 6,000 Kelvin. So as we'll see in a few minutes, this has some huge advantages for excitation of atoms because of the increased heat. And we'll talk about that when we look at the Boltzmann distribution that will help us predict the excitation efficiency of different atoms. Now, when we arrange an ICP with an atomic emission spectroscopy unit, we have our plasma coming up, right? We have a plasma coming up here. And we might be tempted to put our detector either on top, where we might call this axial, or we might put this to the side of the plasma flame. Well, it's not a flame, it's just a plasma. And we would call this a lateral position. So we could put our detector in an axial position or in a lateral position. And the question is, where do we want it? Okay, typically we'll put this at the axial position because we're going to get a longer path length of the analytes as they come up through the plasma. Okay, we get longer path length, which again is going to lead to higher sensitivity. From the lateral, we don't have a full concentration of our analyte the whole way through. It might not be homogeneous because it's going to be more concentrated in the center. And the axial is going to see that highly concentrated area with a much longer path length through that highly concentrated area than your lateral will. So your axial is going to give you a higher sensitivity to the instrument. Sensitivity. There we go. All right, so next take a look at the Boltzmann distribution that's going to explain why this 6,000 Kelvin is so much of an advantage. But before we do that, one last thing with the advantages of the ICP. In addition to getting really good sensitivity from an axial position, we also have very few interferences from the plasma itself. Argon does not absorb or emit light in the same wavelengths that most of our samples of interest are, and we're rarely interested in making an argon analysis. So this means that our background for this plasma is going to be really low at the wavelengths that we're actually interested in for most elemental analysis. And additionally, we have this high temperature. Now, one of the main disadvantages of an ICP, and one of the reasons that we don't use it a lot in our lab, even though we have an ICP, is that argon is very expensive, and we're flowing at a very strong rate of argon that means we're going to go through a lot of it. So this instrument can be fairly expensive to use, as an ICP uses a lot of argon. So it's going to be more expensive than your other options of instruments, but again, we're getting really low interference from the plasma, which makes us have a very low detection limit, and we also get really high sensitivity. So as always, a trade-off with cost.